Yeah. So basically what I'm now going to do is this is almost exactly like what we did over here. Okay, here I'm doing it sideways just because, but it's the same exact kind of idea, which is I take the length of that representative. Here, I'll draw it in. So I get, when I rotate it about the y-axis, I'm going to get a disk. I take the height of that representative rectangle, which is, for a given y value, the x-coordinate is root r squared minus y squared. And I square it, multiply by pi. That gives me the area of that circular disk. I multiply by the thickness. But now, instead of integrating from 0 to r, which would give me the volume of a hemisphere, I now just integrate from h to r. Okay, so this formula for the volume of this spherical cap is going to be in terms of r, but also in terms of h, which is the height at which you passed the intersecting plane. So this will be pi integral from h to r of r squared minus y squared dy. And okay, now we just do it, right? So pi, this becomes, this becomes r squared y. In other words, remember y is the variable we're integrating with respect to, minus y cubed over 3. So this is almost exactly like the previous problem. But now the limits of integration are r and h. So I get, when I plug in r, I get r cubed minus r cubed over 3. So 2/3 r cubed. But then minus, maybe I shouldn't skip steps. So I get pi times, when I plug in r, I get r cubed minus r cubed over 3 minus what happens when I plug in h for y, which is r squared h minus h cubed over 3. And so in fact we get pi times 2/3 r cubed minus r squared h plus h cubed over 3. And that's just really cool that we can find the volume of such a complicated, they pull out a 3 for some reason, 2r cubed minus short. Yeah, it's a really cool, I think, that we can find the volume of such sort of complicated shapes now using the power of integration. Okay, woo, it's like the longest homework ever. 3 more to go, but I think they're just like all hard. 53. I thought for a second, should I assign this problem or not? And apparently I assigned it. This problem is not particularly essential or life-changing in any kind of way. I think I just threw it in there because, well, let's go. Let's just do it really fast. So here we go. 53. Find the volume of a fuel tank. A tank on the wing of a jet aircraft is formed by revolving the region bounded by the graph of y equals 1/8 x squared root 2 minus x about the x-axis. Find the volume of the tank. Okay, and they even sort of draw a little picture of this. So what does it look like? There, it's, okay, by the time this function's only defined, well, it's only, the domain only goes to 2, and in fact 0 is a root, and so it just kind of has this sort of weird shape like that. And if we rotate this about the x-axis, we get some sort of fuel tank. So what's the volume of this fuel tank? Yeah, some of the people in the generation who like invented calculus were inspired to do so via problems like finding the volumes of like barrels of wine and stuff like that. Like well into the 17th century, people just didn't know how to do that. They would just have a gigantic barrel, and the barrel would be containing some sort of high density, economically rich quantity, such as wine, and the shape would be extremely describable in terms of sort of some kind of curve, and it would be completely symmetrical, and they just didn't know how to find the volume of it. The only way to do it was to pour the volume out into some sort of known shape. And so, okay, it's not so crazy to sort of care about finding the volumes of these things. Anyway, this problem is maybe a little bit silly, because it's kind of artificial. Anyway, I need to find the volume of this fuel tank, so we need to find the volume of the shape that results from this little green region being rotated about the x-axis. So that just boils down to, here's my representative rectangle, and I just got a big old integral to do now. And that integral is going to be x squared over 8 root 2 minus x. But then quantity squared dx integral from 0 to 2 pi. Pi r squared times the thickness of the disk, and then add them all up. And here r is just the height of this function. So I just really don't want to do this, but I guess I have to. So what happens, I can take the 64 out, and then get integral from 0 to 2 of, when I square this, this becomes x to the 4th, 2 minus x. So maybe this is not so bad. This is negative x to the 5th plus 2x to the 4th. So I take it back. There wasn't even anything. There's just nothing. There's nothing going on in this problem. Pi over 64. Okay, so let's just do it. Pi over 64 times, negative x to the 6th over 6 plus 2x to the 5th over 5, but then all evaluated at 2 and 0. So what does all that turn out to be? Oh man, I hope this ends up being nice. Oh, I think it will be, because 2 to the 6th is 64. So both these numerators are 64. That's just a fact. And therefore, I can pull that whole 64 out, and this just becomes pi negative a 6th plus a 5th. And the difference between a 6th and a 5th is just 1/30th, right? Because like negative 5/30ths and 6/30ths. So I guess this is just pi over 30. Seems small, but I bet that's just the right answer, because it worked out so nicely. Yeah. Okay. There was no reason why we had to do that problem. 65 and 77, however, are just awesome. What is 65? I think I need to make some space. Okay, so these are each going to take like 10 minutes, and then we're going to be done with this homework. Okay. Whew. Oh boy. Very long homework here. 65. A manufacturer drills a hole through the center of a metal sphere of radius big R. The hole has radius little r. Find the volume of the resulting ring. Oh man. What's going on? I have a sphere. And then, in order to make a hole in this sphere, I drill a hole through the center of that sphere, forming what you might call like a bead, say. What's the volume of that bead? As a function of the volume of the original sphere, the radius of the original sphere, and the radius of the hole that I drilled through the center. Okay, and I think they let big R be, yeah. Okay, so I'll draw a circle, and what am I going to do with this circle? Well, I'm going to sort of drill through it and cut out a certain hole. Okay, and before I erase it, some people who are being very casual might think, oh, isn't this problem just easy? Don't I already know the volume of a sphere? And isn't this shape that I'm cutting out just a cylinder? And so can't I find the volume of this bead by just subtracting the volume of a cylinder from the volume of a sphere? No, because this is not quite a volume of a cylinder. You can even see it from this diagram that this is sort of curvy over here on the edge, right? So this, because of this curvy bit, this shape that we're drilling out is in fact not so simple. Okay, and so I'll now cut this out, and so this is kind of what's left. Although this is maybe a little kind of misleading or something like that. So let's now reconceive of this bead as simply what you get when you take this region and rotate this region about the x-axis. And now I can erase the left-hand side because this is completely symmetric, so I'll just multiply by my final answer by 2. So I take, well, it's actually not so different from the sort of spherical cap problem from before. Okay. So let's start. So this is x squared plus y squared equals big R squared. This was the area of the big circle. And if I'm going to rotate this about the x-axis, which is what you have to do to recover the shape that's being described, note that if I rotate about the y-axis, then I'm getting that spherical cap. If I rotate this green region about the y-axis, I'm getting that spherical cap again. So this is actually like a different shape, right? Obviously, but it's what happens when you rotate a similar kind of region. And how is this region described again? Well, this point up here was 0 big R, and this point over here was little r. So that's 0 little r. Little r is the radius of the hole that's being drilled out from the center of it. Okay. Well, this is sort of the hard part, I guess, is all this kind of understanding. And when you do this, you get this bead. Or at least that's half a bead. Okay. Maybe it's not that hard because what should I do? Well, once I know that I'm rotating about the x-axis, I should draw my representative rectangle. Here is my representative rectangle. And for arbitrary x value, I just need to figure out what happens to that representative rectangle. Well, it's going to form a washer. And so I will find the dimensions of this washer, and then I'll be done. Okay, what are the dimensions of this washer? Well, the inner radius of the washer is in fact a constant. It's just always going to be little r. The outer radius of the washer is just the height of that rectangle, which is just going to be root big R squared minus x squared, is the y coordinate always. And then I think the part that's a little bit subtle is that I really need to know this point over here, because I'm not down over like here or something was big R, but I'm not integrating all the way to big R, because when I drilled through, I cut out some of my shape. So I'm going to integrate only from 0 to whatever that point is. And well, what is that point? It's the point whose y-coordinate is little r. And so I have to take the equation of the circle, x squared plus y squared equals big R squared, and just say, well, what is x when y is little r? And the answer is that x is root big R squared minus little r squared. So here we have two constants floating around. The big R, the radius of the original sphere, and little r, the radius of the hole that we drilled through. And it just is true that that there is this point, root big R squared minus little r squared, which is which is on this curve. And so to do this problem, I need to use the method of washers. I'm going to do pi the outer radius, which is root r squared minus x squared minus the area of the inner circle, which is going to be pi little r squared. That gives the area of the washer, circle minus circle. Then I multiply by the thickness, which is dx, and then I integrate from 0 along the x-axis to that point, root big R squared minus little r squared. And that only gives me half a bead, so I multiply by 2. Whew, okay, so this becomes 2 integral from 0 to root big R squared minus little r squared. I guess there's a pi on the outside here as well, and then that becomes r squared minus x squared minus r squared dx. And, okay, sure, but I think for clarity, we should rewrite this polynomial as negative x squared plus, and I'll put parentheses around this because these are both constants, so that sort of should be thought of as like one big constant. And I think it helps if you do that, it helps to remember how to anti-differentiate properly. What is the antiderivative of all this? Well, it's negative x cubed over 3 plus that thing times x, because it's just a constant, and then there's still a 2 pi on the outside, and then this whole thing is evaluated at 0 and root r squared minus little r squared. Okay, now we get 2 pi times, doing some real math now, that's negative a third. Well, okay, we did something like this already, right? R squared minus r squared, but then like quantity, it's like to the 1/2, but then cubed, so that's like to the 3/2. And then here, it's r squared minus r squared, but then times to the 1, so that's also to the 3/2. So, okay, this is just algebra skills. I did it all out last time, but those are both, okay. So what I end up with is 2 pi times 2/3 big R squared minus little r squared to the 3/2. And okay, I don't know how you want to write that final answer. You could just write it as 4/3 pi r squared minus r squared to the 3/2, and that seems fine, and that's just right. If you really want to be like cool or something, you can say that this is 4/3 pi, and then it's something cubed. What is that something cubed? Well, it's this. In other words, if I were to sort of try to extract some sort of meaning out of this problem, I would say that the volume of this bead is equal to the volume of a sphere whose radius is root r squared minus r squared. So yeah, it's hard to sort of draw a picture of that though, and understand what that means. So like this blue line which I'm about to draw now, that's big R, and this little one is little r, and this horizontal one here is root r squared minus little r squared. And so the volume of this bead is equal to the volume of a sphere which had that as the radius. So that might be something, you could maybe get something deep out of that, I don't know. Okay, almost all the problems done, one to go. This is a very hard homework assignment, I think, because it's geometry, it's picture drawing, it's understanding, and then the intervals are hard too. This is just harder than I thought, and it's just more than I thought it was. But we push on. 77. There are shapes left for us to learn about, and here we go. This problem says find the volume of a torus. Okay, what's a torus? That's a donut, and we need to find the volume of that donut. Man, this is going to be hard. Yeah, it will be hard. They gave us a picture. And what they say is show that the volume of the torus shown is given by blah, 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 blah. Okay, so they drew this picture in the book, so I won't try to redraw it in all the technical glory that they employ. But, okay, I know what makes this problem so hard. It's algebra and understanding and stuff like that. So what they want us to do is to find the volume of a torus with sort of radius of the torus, so to speak, big R, and radius of the torus, little r. Okay, what does that even mean? Take this point, take a circle. I think it's sort of very clear how this should be translated into a calculus problem, which is, especially with their picture, take a circle centered at big R, and let that circle have radius little r. And thus, I can say that the equation of that circle is x minus big R squared plus y squared equals little r squared. And now, rotate that circle about the x-axis, y-axis. And if you rotate that circle about the y-axis, then what you're going to get is, okay, I don't want to draw because it's going to mess up my picture, but does everyone see the circle just going to go and it's going to form a torus? Okay, I need to find the volume of this torus. How? Well, first of all, I am committed to only finding the volume of the top half of the torus and then multiplying by 2. So let me now understand that this point is big R plus little r, comma 0, and that this point here is big R minus little r, comma 0. And if this is my shaded region, well, I can save time by only finding the volume of the top, by only finding the volume of the sort of the top half of the bagel, so to speak. And you can't cut any more corners because you might think, oh, can I just look at this quarter circle? But no, because actually there's more volume when the right quarter circle gets rotated around the y-axis than when the left quarter circle gets rotated around. Because all of those representative rectangles have like larger radius than all those do, although that's sort of not totally obvious. Okay, so there's no sort of shortcut here. I have to really rotate that entire green semicircle about the y-axis, and that's going to produce a half of a torus, the top half of a torus. Okay, and I think what makes this hard now is sort of visualizing this, understanding it, and realizing that this is what you need to do, but then also coming up with the, well, okay, so that's my representative rectangle. That's what happens when I rotate this representative rectangle. I get the big washer, and now I have to figure out what the dimensions of those what that washer is. Well, since I'm rotating about the y-axis, I'm going to be taking an arbitrary y value. And now what I need to do is I need to solve for, I need to know what this point is here, and I need to know what this point is here. Okay, well, what are those points? Well, here is, I think, well, okay, so if you try to solve for x effectively is what we need to do, right? Because I need to find what are the x coordinates for a given y. Well, if you go to solve this for x, then you get, okay, you get x minus r squared equals little r squared minus y squared. Then you take the square root, but like, you have to be careful, right? Because when you take the square root, you get really like plus or minus root r squared minus y squared. And I think we're just not as used to thinking of in this way, right? We are somehow, when it comes to semicircles, because they're functions, we're pretty comfortable with thinking of that as y equals root r squared minus x squared, and then also thinking of the bottom semicircle as y equals negative root r squared minus x squared. But we're less comfortable thinking of sideways semicircles. So this semicircle is x equals root r squared minus y squared, and the like left semicircle is x equals negative root r squared minus y squared. And here, both of those are relevant because we really do have like a kind of a different equation for the right half semicircle and the left half semicircle. And that's sort of borne out here in the algebra, that because this is really like x equals big R plus or minus root r squared minus y squared. Okay, so what am I talking about? What I'm talking about is that the inner radius, the distance to this left endpoint here, is in fact big R minus root little r squared minus y squared. And the outer radius, that's consistent with that being the like sort of the left semicircle, so to speak. And the outer radius is big R plus root r squared minus y squared. All right, and if you understood and followed all of that, then finally we can do this problem. How? Maybe I want to write this way. Okay, so I'm going to say take pi times the outer radius, so that is r plus root r squared minus y squared squared. So that's the area of the large circle, minus pi times, and now cha-cha, we find the area of the inner circle, which is going to be big R minus root r squared minus y squared, cha-cha-cha. And then that whole quantity is going to be multiplied by dy, and then we're going to integrate up the, times dy, yep, and then we're going to integrate up the y-axis from 0 to, that's just little r, where we stop. And then we multiply by 2. Okay. Whew. I don't know if I needed to go through both boards here, maybe I do, because this becomes 2 pi, integral from 0 to little r, of, just multiply this out, what do I get? R squared plus 2 big R root r squared minus y squared, plus, and now when you square that, you just get r squared minus y squared, but then minus, so that whole thing was like the first one, minus, well, what happens when you square this, because that is squared, well, you get big R squared minus 2 big R, r squared, root r squared minus y squared plus r squared minus y squared. Cha, and then there's a dy over here. Okay, that is just me squaring those two binomials that are in brackets. Okay, but now, just like a million things cancel, right? This r squared cancels with that r squared. And then these cancel, and these cancel as well. And so, what do we get? We get 2 pi integral from 0 to little r of 2 big R root r, well, I'll just write it. 2 big R root r squared minus y squared, and then there's just like another one over here, right? Plus another 2 big R root r squared minus y squared. And so, dy. Okay, so what we end up with is 4 pi big R squared times the integral from 0 to little r of root r squared minus y squared dy. And that was, in fact, part A said, it gave you this formula, and it said show, how did they get that 8? I'm off by a factor of 2 somewhere. 2 and 2, oh, because 2 and 2 is 4, and I'm supposed to add. So 2 of these plus 2 of these is 4, so I factor a 4 out of here. There was already a 2 here, so there's 8. Okay, good. So, good, this is like correct. For part B, it says, dude, just finish it off by doing this integral. And okay, we've seen this trick before, right, from the previous video. This is just the area of a circle of radius r. And if I'm integrating from 0 to r through root r squared minus y squared, well, that's just going to be pi little r squared over 4 times 8 pi big R squared. And so, that's my final answer. Okay, so my final answer to this problem is, well, if you didn't understand this because you didn't watch the previous video or something, you know, this integral from, if that's r, and that's 0, r, and that's r0, and if you take a semicircle, that's just the area of a quarter circle of radius r, but that's just the equation of, right? I guess this way we'd be integrating like this way or something, right? So okay, because this is the circle x squared plus y squared equals little r squared, and so that we just know by geometry to be a quarter of a circle of radius little r. Okay, so what's our final answer? Our final answer is 2 pi squared. Sorry, something went wrong. Oh my god, I'm double stupid because I squared. Oh my god, okay. 2r plus 2r is just 4 big R, so that's just a single big R. Okay, I had some dimensionality problems there, so it's 2 pi squared big R little r squared. I mean, that's just the answer. I don't even have to check it because I just know and understand this formula, but I keep messing up, so I'll do that. Okay, so great. Have I like enriched my life at all with this knowledge of the volume of a torus? Well, a little bit, because I would now like to convince you that you knew this formula all along, that this formula is in fact just like obvious, and is the exact formula that you would expect it to be if you were ever going to make a torus. And let's say you were doing some baking, like let's say you were making a donut, or like a bagel. How do you make a bagel? Well, you start with a cylinder. And you start with a cylinder that's long enough that you put it, then you sort of get the dough all wet or whatever, and you just kind of wrap it around and you make a torus. In other words, you start with a cylinder with a radius little r, and of course then what will the length of this cylinder be in terms of the overall radius of the bagel that will result? Well, it's just going to be the circumference. So this is going to be just 2 pi big R. And, well, what is the volume of this cylinder? It is just, the volume is just pi r squared, the area of the base, times the height, times 2 pi big R. Okay, and so the best way to report the volume of a torus is to just sort of write it as pi r squared times